The paper presents a comprehensive study of the Magnetar-Like Outburst of PSR J1846-0258, a rotation-powered pulsar, observed in August 2020 using the Neutron Star Interior Composition Explorer, NICER, and NuSTAR. The outburst was characterized by a large spin-up glitch, a significant increase in pulsed flux, and a transient thermal component in the spectrum. The authors report on their long-term monitoring of PSR J1846-0258 using NICER, which provided phase-coherent timing solutions from March 2017 to November 2021, including a coherent solution throughout the outburst. They detected a large spin-up glitch of magnitude dn, nu equals 3 × 10⁻⁶, at the start of the outburst and observed an increase in pulsed flux that reached a factor of more than 10 times the quiescent level. Spectral analysis of the pulsed emission of NICER data shows that the flux increases result entirely from a new blackbody component that gradually fades away while the power law remains nearly constant at its quiescent level throughout the outburst. Joint spectral analysis of NICER and simultaneous NuSTAR data confirms this picture. The authors discuss the interpretation of the Magnetar-Like Outburst and origin of the transient thermal component in the context of both a pulsar-like and a Magnetar-like model. They highlight the similarities between PSR J1846-0258 and PSR J11196127, another rotation-powered pulsar that has exhibited magnetar-like outbursts. The study is significant as it provides insight into the blurring of the dividing line between rotation-powered pulsars and magnetars. The authors suggest that the MeV pulsars, a group of rotation-powered pulsars that exhibit strong, non-thermal hard X-ray emission, may be a bridge between these two populations. The paper also presents details of the observations and data reduction procedures, including the processing of NICER data using HEAS often NICERDAS, and the filtering and screening of events for timing and spectral analysis. The authors discuss the limitations of their study, including the gaps in the NICER monitoring due to visibility constraints, and suggest future work to investigate the connection between rotation-powered pulsars and magnetars. Here is the combined summary. The research focuses on the 2020 outburst of J1846-0258, a magnetar-like pulsar. The authors utilized NuSTAR and SWIFT data to analyze the spectral properties and timing behavior of the source during the outburst. The NuSTAR data were reduced using the standard data reduction process, and the spectra were extracted from circular regions of 1 foot radius centered at the source position in the 370 keV energy band. The spectral fitting was performed using the GRPPHA tool, ensuring each spectral bin had a minimum of 25 counts. The SWIFT monitoring campaign of J18460258 started on July 25, 2011, and ended on November 19, 2018. The authors analyzed the monitoring data collected between September 17, 2016, and November 19, 2018, to characterize the spin behavior of J18460258 during its quiescent state before the 2020 outburst. On August 1, 2020, the SWIFT telescope reported a short-duration flare in the BAT detector from J18460258, prompting 2 observations with NICER, which obtained densely sampled observations of the source until November 22, 2020. The 2.510 keV pulsed count rate showed a significant increase by a factor of ~4 with respect to the quiescent level, indicating the source had already gone into outburst between May 27, 2020, and June 26, 2020. The authors performed timing analyses of the pre-outburst, outburst, and post-outburst episodes using NICER and SWIFT monitoring observations to make comparisons between quiescent and outburst states possible. These analyses yielded phase-coherent timing models in terms of 3, sometimes 4, timing parameters specifying the frequency nu, frequency derivative, nu, frequency second derivative diaresis nu, and third-order nu derivatives evaluated at a certain epoch t. The models accurately describe the rotation behavior of the pulsar as a function of time, enabling the tracking of the spine volution of the source. Pulse phase folding timing data from any instrument using these ephemerides, adopting different energy selections, yielded energy-resolved pulse phase distributions, often called pulse profiles. From these, the pulse shape as a function of energy can be determined for any emission state of the pulsar. The models also enable the separation of the pulsed emission component from the total emission, allowing the study of the pulsed flux as a function of time, probing the outburst. The paper presents a detailed analysis of the timing behavior of the Magnetar PSR J1846-0258, focusing on the 20,172,021 period. The authors have derived phase-coherent ephemerides from NICER and SWIFT XRT monitoring data, which are presented in Table 1. The ephemerides cover the pre-outburst, outburst, and post-outburst periods, with the outburst occurring in 2020. The spin frequency evolution of PSR J1846-0258 is shown in Figure 2, which reveals several timing discontinuities, including glitches and phase coherence losses. The authors have identified 6 distinct events, including a strong glitch in 2020 that heralded the start of the outburst. The breaking index of the pulsar before the outburst is measured to be 2.7 plus or minus 0.2, indicating a return to its original pre-2006 outburst evolution. The authors have also investigated the pulse profile evolution of PSR J1846-0258 during the pre-outburst, outburst, and post-outburst periods. Pulse phase distributions are presented for several energy bands, showing the well-known pulse shape of the pulsar. The pulse phase distributions are similar in shape and strength during the pre-outburst and post-outburst periods, but differ during the outburst episode. The analysis reveals that the pulsar's rotation frequency evolution is complex, with multiple glitches and phase coherence losses. The breaking index measurement suggests that the pulsar's rotation has returned to its pre-2006 outburst state. The pulse profile evolution study provides insights into the pulsar's emission mechanisms during the different periods. The results of this study have implications for our understanding of magnetar behavior and the physics of neutron stars. The research focuses on the Magnetar J1846-0258, particularly on its 2020 outburst and spectral evolution. The study utilizes observations from SWIFT, NICER, and NuSTAR to analyze the pulsed emission across different energy bands. Pre-outburst observations show weak pulsed emission in the 1–2.5 keV band, mainly from events with energies between 2–2.5 keV. During the outburst, a strong soft pulsed emission component emerged, gradually fading away towards its quiescent level. The pulsed significance in the 1–2.5 keV band decreased from 31.5 sigma to 6.0 sigma across the outburst segments. Contrary to the quiescent state, a prominent shoulder or bump appeared in the pulse profiles during the first segment of the outburst, which faded away. The pulsed emission above 10 keV remained relatively constant. The study also discusses the spectral evolution, performing joint fits on NICER and NuSTAR spectra at 4 epochs to examine the broadband spectral behavior of the pulsed emission. The research paper discusses the X-ray outburst of PSR J1846-0258 in August 2020, which was the second Magnetar-like outburst since its discovery in 1999. The study utilized NICER GO and 2 observations for continuous monitoring and timing of the source, starting 3.5 years before the outburst until more than a year after it in November 2021. The pre-outburst monitoring observations showed that the flux began to increase above the quiescent level by late June 2020. High-cadence observations during and following the outburst resolved rapid changes in the pulsed flux, which increased by more than a factor of 10 above the quiescent level. This increase in flux is higher than the 5 times increase reported for the 2006 outburst, although the flux during that outburst was less densely sampled and timing coherence was lost. The paper also presents the results of joint NuSTAR-NICER observations, where the best fit parameters are provided in Table 2. The photon indices varied slightly but remained consistent at around gamma approximately equals 1.2, while the blackbody component varied significantly, indicating that the flux variability during the outburst is dominated by changes in the blackbody component. This can be seen from the pulse profiles as a function of energy in Figure 5. The spectral evolution in the soft X-ray band was traced using all NICER datasets. By freezing the NH at 6.1 × 10⁻22 square centimeters and the gamma at 1.2, the unabsorbed fluxes in the 110 keV band, fluxes of individual components in the same energy band, and 3 spectral parameters were determined. The overall flux, kTBB, and blackbody flux decreased over time, with a mini flare observed on MJD 59082, August 21. During the flare, the kTBB and flux increased. A few days after the flare, the blackbody component could not be well constrained, and the power law dominated the spectrum in the soft X-ray band. The study highlights the importance of continuous monitoring and timing observations for understanding the spectral evolution and outburst phenomena in magnetars like PSR J1846-0258. The findings suggest that the outburst is dominated by the increase of the surface emission, and the power law component remains constant throughout the entire observation run. Here is the combined summary. The spectral evolution of the pulsed emission of J18460258 observed with NICER following the outburst on 2020 August 1 is presented in Figure 7. The figure shows the evolution of the unabsorbed flux in the 110 keV band, blackbody temperature, emitting radius, BB flux, PL flux, and the ratio of BB flux to the total flux. The characteristics of the 2 magnetar-like outbursts of J18460258 are very similar, with both outbursts accompanied by spin-up glitches of similar size and transient thermal components responsible for most of the flux increases. The thermal components and flux also decayed over similar timescales of several months. PSR J18460258 appears to be a unique and fascinating source with a dual nature, behaving most of the time like a rotation-powered pulsar, RPP, and occasionally like a magnetar. It is also an unusual young RPP, having no detected radio or JV emission. The quiescent behavior as well as the outbursts can be interpreted in either a pulsar-like model or a magnetar-like model, but involve very different physical mechanisms for the emission. In the pulsar-like model, the lack of radio or JV emission is due to geometry, with MeV pulsars having global dipole magnetospheres that are nearly force-free, emitting radio emission from above the magnetic poles and gamma-ray and non-thermal X-ray emission from near the current sheet outside the light cylinder. The magnetar-like outbursts are due to the appearance of or a change in a toroidal surface magnetic field component that provides a field twist, and more particle acceleration and pair production near the surface. In the magnetar-like model, the quiescent X-ray emission from J18460258 is resonant inverse Compton scattering emission from particles accelerated by field twists and scattering thermal photons from the hot neutron star surface. The outbursts are then typical magnetar bursts where crustal motions cause increases in the magnetic field twists, particle acceleration, and RICS emission. The increased particle acceleration and pair splitting cascades produce visible heated spots due to particle surface bombardment. Table 3 presents the best fit parameters of NICER observations, including the blackbody temperature, emitting radius, BB flux, and PL flux. The table shows the evolution of these parameters over time, with the flux peaking around MJD 59100 and then decaying. The parameters are consistent with a thermal component dominating the emission during the outburst. The research discusses the properties of J1846-0258, a neutron star that exhibits both pulsar-like and magnetar-like behaviors. The authors propose that this object might be part of a continuum between radio-quiet pulsars, RPPs, and magnetars. They argue that the lack of a significant thermal component in its quiescent emission could be due to its magnetic activity not being persistent enough to produce heated spots. The paper also notes that the X-ray luminosity of J1846-0258 is less than its spin-down power, unlike magnetars, which have an X-ray luminosity that exceeds their spin-down power by several orders of magnitude. The authors suggest that continued X-ray monitoring and expanded spectral coverage are crucial for understanding its true nature and place in neutron star evolution.